Now I'm going to explain this article predicting the semantic textual similarity between Siamese CNN and LSTM in 2018. And semantic textual similarity is the basis of many applications in natural language processing. Our system combines convolution and recurrent neural networks to measure the semantic similarity of sentences. It uses a convolutional network to take account of the local context of words and an LSTM to consider the global context of sentences. This combination of networks helps to preserve the relevant information of sentences and improves the calculation of the similarity between the sentences. So semantic text similarity is an important task in NLP, and it has applications such as information retrieval, classification, extraction, question answering, and plagiarism detection. The STS task measures the degree of similarity between two texts and can be expressed as follows. Given two sentences, a system returns a continuous score on a scale from 1 to 5, with 1 indicating that the semantics of the sentences are completely independent and 5 meaning that there is a semantic equivalence. STS is a difficult issue since languages have numerous ambiguities and synchronous expressions, while sentences may have variable lengths and complex structures. So a sentence is composed of words which can form phrases. Examining a sentence and its components helps us to comprehend its meanings. So this is the architecture of Siamese CNN LSTM to calculate the similarity of pair sentences. So we have one token and the surrounding variables. So these are the surrounding tokens in this sentence. And so these are the surroundings around this. So we give it to convolution, and so we have a representation for sentence A and sentence B. And again, to use this similarity, e to the minus semantic similarity between embedding between sentence A and sentence B. And this is L1 norm. L1 norm is more important than L2 norm because experimental results has shown that we should use L1 norm. So a local context of length K, for example, length L, for example, 5, can be written as this. So we are concatenating. So this is the center, ice word, and the surroundings. So we have a context. Context has length 5. 1, 2, 3, 4, 5. And then our CNN generates the local context of word I. And so this is the local context. This is the bias that we should learn. This is the weight that we should learn. And in order to analyze the general and local context, we concatenate its pre-trained word embeddings and its local context. So our LSTM updates its state and produces output H sub I at time I in a sentence. So this is a Siamese LSTM that we see the mean squared error for different models that we use, different methods that we use. And we can compare, for example, this one with ConvNet. And so we have a pair of sentences, and we know the gold score. This one is fish is being cooked by a woman. So these are very similar, and this one is not similar. It's around 0, and this one is around 5. So Siamese LSTM shows this one, but the approach calculates the 4, so it is closer to the gold score. So our approach is closer to the gold score. So another example, this one is closer to the gold score than the Siamese LSTM. So it's a so this approach is a slight improvement of the Siamese LSTM.